Imagine for a moment, maybe you're running a delivery business or, just planning a big family road trip. Every single mile, every minute, every bit of fuel, it all counts, right? So what if you had a system that could instantly figure out not just the fastest way, but the absolute cheapest, most efficient path? And it adapts in real time to sudden traffic jams or fuel prices jumping up or even like a surprise storm. Today, we're taking a deep dive into this fascinating world of the Best Route Finder API.
Yeah, and this isn't just your standard navigation app, like the one on your phone. Our mission here in this deep dive is really to unpack the source material you've provided us. We want to understand the goal, the real objective behind such a powerful API. We'll dig into how it uses all that real-time data, plus some pretty cutting-edge machine learning to actually deliver those optimized routes. And crucially, why this tech is becoming such a game changer for businesses, and maybe even for individuals just trying to save time and, importantly, money on the road.
Okay, let's start right there then. Let's unpack it. If I'm, say, a logistics manager, what's the core problem this Best Route Finder API is really trying to solve for me?
The objective is actually beautifully clear. It's to build an API that gives users the cheapest and most optimal route. That's the key. And it doesn't matter if it's for one trip or managing a whole fleet across tons of destinations. How does it do it? Well, it cleverly blends real-time data like what's happening right now on the roads with historical data, insights from past trips. That makes it super dynamic. So for that logistics startup you mentioned, this means optimizing delivery routes literally on the fly. It finds the most cost-effective path by looking at tolls, current fuel costs, live traffic, even the weather forecast. It can even give you a ranked list of the best options, each one with a clear score so you can weigh the pros and cons.
So it's way beyond just speed. It's about making really smart decisions out there. And for the person actually using it, what kind of info do you need to feed into this thing, and what does it actually give back?
Exactly, smarter decisions. So you, the user, you input the basics. Your starting point, your destination. But then you add the live parameters you care about, maybe current traffic, real-time weather updates, specific toll info, what you're paying for fuel right now. And in return, you get that cheapest, most optimal route. And it's not just a guess. It's backed by the sophisticated mix of real-time prediction and deep historical learning from tons of past data. The real power is making every single journey count, financially and efficiently.
That makes a ton of sense, especially thinking about how much things like fuel and traffic can change day to day, even hour to hour. So what are the really concrete benefits? What stands out when you use this kind of intelligence?
Yeah, the variability is key. We see several major benefits. First, real-time cost prediction. It's not just estimating time, it's predicting the actual cost in dollars and cents, which is huge for budgeting. Second, accuracy and optimization through ML models. This is the AI magic, constantly learning, constantly getting better. Then you've got API scalability. Because it uses managed serving layers, it can handle like a massive number of requests without slowing down. Very important for big operations. There's also fantastic cost and route transparency. It logs everything, toll costs, fuel use, so you have a perfect audit trail. No mysteries. And finally, easy governance. Tools like Unity Catalog and MLflow make managing the data and the models straightforward and trackable.
Okay, that definitely sounds like it needs some serious brain power behind it.
Yeah.
How does the system actually know the best route? What are these machine learning models doing under the hood? What's making these predictions?
Right, this is where the predictive intelligence really kicks in. Typically, you have two main ML models working together, sort of like a team. First, there's the rate cost predictor. You can think of this one as the brain that predicts the likely cost between any 2 points on the map. It uses some pretty powerful algorithms, maybe things like XGBoost or random forest. These are basically advanced pattern finders, really good at spotting complex relationships in data. And they look at inputs like distance, estimated time, fuel needed, tolls, current weather, traffic congestion, all that jazz.
Okay, so that predicts the cost. What's the second model?
The second one is the best redder ranker. So once the system has a few possible routes, this model steps in to rank them for overall optimization. It might use algorithms like LightGBM or maybe logistic regression. These are known for being super efficient at sorting through options and making smart comparisons quickly. And this ranker considers not just the predicted cost from the first model, but also the ETA, the estimated time of arrival, plus any potential risks, maybe user preferences you've set, and even how severe the weather might be along each route.
Wow, that's a lot of factors to juggle. How can we be sure these models are actually reliable, that they keep getting better over time? How do you trust the outputs?
That's a really critical question. MLflow registry is absolutely key here. Think
Yeah.
of it like a central library or maybe a version control system specifically for your AI models. It's where you register and version every model you train, so you always know exactly which version is running in production. It also logs vital evaluation metrics, things like root mean squared error or RMSE and R accuracy. These tell you precisely how accurate the predictions are. And what's really cool is that every single API call, every time someone requests a route, that request and its outcome get logged to a Delta table. Think of Delta tables as super reliable version ledgers within your data lakehouse. This logging is crucial. It's essential for governance, for auditing costs later on, and maybe most importantly, it provides incredibly valuable data to feed back into future model training. It creates this continuous improvement loop.
Huh. It's fascinating how just using the system helps make it smarter. But all this intelligence needs fuel, right? And that fuel is data. What kind of data are we feeding into these models, and how does it get prepped? It can't just be raw feeds, can it?
Exactly right. Data is the fuel. The journey that data takes often follows a pattern called the medallion architecture. It's a common best practice in data platforms like Databricks. It starts with bronze tables. This is where the raw source data lands, ingested straight from providers. Think real-time traffic APIs, maybe Google Maps distance matrix for distances, fuel cost feeds, weather services, toll information providers. It's raw, untouched. Then, that raw data gets cleaned up, it's validated, deduplicated, maybe some basic transformations happen, and it lands in silver tables. Think of silver as refining the raw ore. Structured now, normalized, much higher quality, easier to work with. And finally, we get to the gold tables. These store the highly refined, aggregated features that are specifically prepared for the machine learning models to train on. Things like distance Gallman, toll cost, calculated fuel cost, maybe a traffic level score, and a weather score. This structured approach ensures the models get consistent, high-quality input.
I noticed in the materials, road tide is mentioned as part of the data. Is that actually used when training the model? It feels like it could be pretty important, linking everything together.
That's a really sharp observation, and it actually highlights a key best practice in machine learning. While route is definitely an identifier, like a unique key for each potential route, and it's absolutely essential for things like logging, tracking requests, and auditing, it's deliberately not used as a predictive feature during model training. Why? Because including it can actually hurt the model's ability to generalize. It might start memorizing patterns tied to specific route IDs, which isn't useful for new unseen routes. It could even inadvertently leak information about the target variable if the ID somehow correlates with cost or time in the training data. So yeah, it's kept in the feature table absolutely needed for joining data, for logging, for audit lineage, but it's explicitly excluded when we actually train the predictor or the ranker model. We want the model to learn general patterns, not memorize specific IDs.
Okay, that makes sense. Avoid overfitting to specific examples. Now, our source material really points to Databricks being the core platform for building this kind of API. For someone maybe not super familiar with Databricks, what makes it so central here? Why choose that platform?
Right, the core value of Databricks in this context really comes down to its unified Lakehouse platform. What that means is it simplifies the whole end-to-end process, from getting the raw data in to cleaning it, engineering features, training complex models, and deploying them reliably. It handles that entire life cycle. The combination of its integrated feature store, which is like a central pantry for all the clean data features the models need, and MLflow for managing the model lifecycle ensures that the machine learning pipelines are repeatable and governed. This is huge for businesses. It means they can actually trust the predictions because they know exactly how the models were built, what data they used, and how they've evolved over time. Plus, it handles real-time inference really well with auto-scaling capabilities and version models, so it's always ready, always performing, even when demand spikes.
That unification sounds incredibly valuable, avoiding patching together lots of different tools. So if we look at the architecture components described for someone thinking about building a system like this, what are the main pieces they'd be putting together? Can you walk us through the key parts?
Yeah, sure. At a high level, think of it like this. First, you've got the client or API consumer. That's the application, maybe a web app, a mobile app, or even another back-end system that needs the route calculation. These requests usually don't hit Databricks directly. They go through an API layer first. Think of services like Azure API Management or AWS API Gateway. This layer acts as the front door, handles security, authentication, maybe rate limiting to prevent abuse. Then all the real work, the data processing, the ML training, the predictions, happens inside the Databricks workspace. That's the unified environment. Data gets into the workspace via an ingestion layer. Tools like Databricks Autoloader are great here, especially for handling streaming or frequently arriving data like traffic feeds. This data gets stored in the storage layer, typically cloud object storage like S3 or ADLS, but managed through Delta Lake and Unity Catalog. Delta Lake gives you reliability, transactions, time travel on your data. Unity Catalog handles governance, lineage, access control. Then you have feature engineering, where you create those predictive features we talked about. Those features feed into the ML model component, where models are trained and registered using MLflow. Model serving is the part that takes a trained model and exposes it as an API endpoint within Databricks, ready to make predictions. And finally, you need scheduler orchestration, maybe Databricks jobs, to automate tasks like data refreshes or model retraining. And monitoring and logging keeps an eye on everything, from API usage to model performance drift.
Okay, that paints a clear picture of the components. So how does the actual data flow through this system? From those raw, messy feeds to the point where it gives us an actionable insight like that best route.
The data ingestion pipeline is really the circulatory system here. It starts by pulling data from all those diverse sources, real-time traffic APIs, maybe the Google Maps distance matrix API for baseline distances and times, fuel cost feeds, weather services, toll databases. Tools like Databricks Autoloader or structured streaming then efficiently ingest this raw data. Often it lands first in cloud object storage, S3, ADLS, GCS. A key step early on is converting this data into the Delta format. That gives you the reliability and performance benefits. These Delta tables are usually partitioned maybe by date or region to make querying faster, and they're meticulously cataloged using Unity Catalog. This tracks the schema, its evolution, and controls who can access what data. Super important for governance. Then that data flows through the medallion architecture we discussed earlier: bronze, raw, silver, clean, structured, and finally gold, aggregated, feature-rich datasets. By the time it hits the gold layer, it's perfectly prepped, ready to be used for training those sophisticated machine learning models or for serving predictions.
All right, so we've got the clean, feature-rich data in the gold layer. We've got the model concepts like the predictor and the ranker. How do we actually train these models? And then critically, how do we make them available so that our logistics manager's app can actually call it and get a route?
Great question. It starts with feature engineering, taking those gold tables and selecting the most relevant features for the specific prediction task, creating your final training dataset. Then comes model training. You'd use a library like scikit-learn or Spark MLlib. For example, you might train a random forest regressor. If using scikit-learn, you often convert your Spark data frame to a pandas data frame first, as that's what scikit-learn expects. During this training process, you absolutely log everything with MLflow. Key metrics like mean absolute error, MAE, root mean squared error, RMSE, they get logged. The model parameters get logged. And crucially, the trained model artifact itself gets logged. After training, you evaluate and register the model. You compare its performance metrics against maybe previous versions or a baseline. If it looks good, you register it in the MLflow model registry. This registry lets you manage model versions systematically. You can promote models through different stages, like from staging to production. This ensures only properly tested, approved models are actually used to serve live requests.
Okay, so the model is trained, validated, registered, sitting there in production stage. How does an external application like that delivery app actually talk to it to get a prediction in real time?
That's where model serving kicks in. Databricks model serving takes that registered ML model and essentially wraps it up, making it available as a standard REST API endpoint hosted and managed by Databricks. So your application can just send a standard HTTP request, usually a PST request, to this endpoint. The body of that request would contain the input features the model needs, maybe formatted as JSON, things like the calculated distance, the estimated toll cost, current fuel cost, the traffic level score. The model serving endpoint receives this, feeds it to the loaded model, gets the prediction back, like that cost prediction of, say, 475.23, and it sends that prediction back to the calling application in the response. The business interpretation then is crucial. That 475.23 number directly answers, okay, based on current conditions and historical data, how much is this specific route likely to cost? And that number can drive decisions. Logistics optimization, showing an estimated fare in a ride-hailing app UI, informing transport planning. Lots of uses.
Got it. So Databricks handles serving the model internally. But how do you expose that capability securely to the outside world, to those client applications?
Right. You typically don't expose the raw Databricks model serving endpoint directly to the public internet. Instead, you'd expose the API endpoint through an API gateway or management layer, like we mentioned before, Azure API Management, AWS API Gateway, GCP API Gateway, or similar tools. Often, you'll build a lightweight wrapper application, maybe using a framework like FastPI or Flask in Python that sits between the API gateway and the Databricks model serving endpoint. This wrapper can handle things like request validation, maybe some final data formatting, and then it makes the call to the internal Databricks endpoint. The API gateway layer then handles all the external-facing concerns: secure authentication, like API keys or OAuth2 tokens, rate limiting, request response transformations if needed, logging external traffic, and generally protecting your backend service. It makes access secure and scalable.
Okay, this is starting to sound like a pretty complex system with a lot of moving parts and definitely handling sensitive data like costs and routes. How do you keep everything running smoothly, reliably, and really importantly, securely?
Absolutely. Orchestration and automation are vital. You can't manually run all these steps constantly. Databricks jobs or workflows are used for this. You'd set up scheduled jobs to, say, refresh your feature tables from source data every hour, or maybe retrain your main prediction model every night using the latest data. Automation is key for consistency. Then there's monitoring and governance. This is multifaceted. You use MLflow logs to track model accuracy over time and detect model drift. That's when a model's performance starts degrading because the real world has changed. Unity Catalog plays a huge role in monitoring who is accessing which data tables and tracking data lineage. Databricks audit logs track who is using the model serving endpoints and other platform activities. And your external API gateway logs are crucial for monitoring client-side API performance latency, error rates, traffic patterns. Finally, security and access control have to be baked in everywhere. API authentication, as we said, uses strong methods like OAuth2 or API keys managed securely. Data access itself is controlled granularly using Unity Catalog's access control lists, ACLs, defining exactly who can read or modify which tables or schemas. Sensitive information, like API keys for external services or database passwords, should be handled securely using something like Databricks secret scopes, not hard-coded. And endpoint security often involves network-level controls like IP allow listing, only letting requests from trusted IPs, and setting throttling limits in the API gateway to prevent denial of service attacks or runaway costs. Security is layered throughout.
It's definitely clear this isn't just a theoretical concept. Are there actual big-name companies using this kind of sophisticated route optimization at scale today? Can you give us some examples?
Oh, absolutely. This technology is really at the core of many services you probably interact with regularly. Think about Uber. Their whole system relies on a powerful route optimization engine. It's constantly choosing efficient routes based not just on time, but real-time traffic, estimated costs like fuel and tolls, and also crucial metrics like time to pick up for the driver and time to drop off for you. It's all driven by ML models predicting ETAs and costs. Amazon Logistics, particularly for Prime deliveries, is another huge example. They have incredibly complex optimization problems balancing cost, delivery speed, package priorities, driver schedules. They use dynamic rerouting constantly based on live traffic and weather, all built on massive big data infrastructure and custom machine learning models. And Walmart Global Tech is doing fascinating work here too. They use a dynamic routing platform not just for home delivery, but also for optimizing in-store pickup logistics and their entire supply chain movement. They factor in traffic, time, fuel, but also complex things like cold chain constraints, making sure refrigerated goods stay cold. Their platform leverages Spark, Databricks, MLflow, and even real-time data streams from Kafka.
Wow. What's really striking about those examples is how they demonstrate this isn't just about finding the quickest way from A to B anymore. It's about finding the truly smartest way, considering cost, efficiency, maybe even environmental impact. It's fundamentally changing how decisions get made across huge industries like logistics, ride-sharing, and all kinds of transport planning. It's quite transformative. So after diving deep into all this, what does it really mean for you, the listener? We've explored how this best Route Finder API idea blends live data, pretty powerful machine learning, and a solid platform like Databricks to dynamically predict the most cost-efficient routes. It's really about using predictive intelligence to make every single journey count, not just for giant corporations, but maybe, potentially, for our own personal travel choices too. It turns guesswork into something much more like data-driven certainty.
And that leads to a really interesting question to ponder. Think about your own daily life, or maybe your business, or the services you rely on. Where could this kind of dynamically optimized, cost-effective routing, powered by this level of intelligence, make the biggest difference for you? Is it in your daily commute? Could it make local deliveries cheaper or faster? Could it even change how emergency services are routed in your city? Where do you see the impact?
Yeah, could this type of predictive intelligence really reshape how we think about, say, urban planning, or the sheer efficiency of all the delivery vans we see, or even just how we choose our own routes day to day? Moving beyond just finding the fastest path to finding the truly smartest one for our wallets, for our time, maybe even for the environment. It's not just about getting there anymore, is it? It's about making the journey itself optimal in every possible sense. Something to think about.